Okay, kids, here we go. There was a man by the name of Michael Faraday. Michael Faraday. We all know that a Faraday would make a lot of cotton candy. A fair a day. That's a lot of cotton candy. Okay. Michael Faraday, he did a lot of stuff. He was in the 1800s, so lots of things. He did stuff with freezing and cooling, with refrigeration, but he's probably most famous for the electric field idea that he came up with. Math wasn't his strong point. He had other smart friends with math, but he is very conceptual and was able to come up with what are called electric field lines to represent what goes on with an electric field. Okay, right now, are you in a gravity field? Are you?
Yes, I am. If I jump off the building.
Don't do that.
Yeah, I won't. I'm just saying.
Okay, Billy, I'm scared.
I'm just saying if I did, then I'd fall down and get boo-booed.
Yeah, exactly, because gravity would pull you down because you're in a gravity field. So if we describe the gravity field, here's Earth, and the gravity field would be down. We'd have arrows that represent the gravity field that we are existing in. And if you put something out here and let it go, boom, falls down to the earth. So the gravity field is always down into the earth. All right, now with the electric field, so let's do an electric field. Well, Faraday knew that there were two different kinds of charges. And we all know what those are.
MasterCard and Visa.
Billy, that was funny. That was a joke like I would say. Billy's starting to think like I am. Kind of scary. Sorry about that, Billy.
Oh, it's okay. You have great jokes.
Billy, I like you. Okay, now, yeah, positive and negative. Those are our two different kinds of charge. So positive can attract or repel things. A positive would attract a negative but repel a positive. A negative can attract or repel things. A negative would attract a positive but repel a negative. And so Faraday said, with gravity we would draw a field always into the earth or whatever planetary body it is. But with electric fields, everything's not going to be pulled in. So how are we going to solve this dilemma? Scratch, scratch, scratch. And Michael Faraday said, well, I'm a man, I'm calling it. Here's what he did. He called it this. He said that the electric field is defined as what a positive would do. A positive, and actually, that's a positive, they call them test charge. A positive test charge. A test charge is something that's really small and is just meant, you think about a test charge as something you would put into the field just to see what happens to it. So a test charge it's small, it would exist, but it doesn't have a lot of mass and it doesn't have a lot of charge, so it's not going to influence the field that's being created around this other particle. So a test charge, so he defined as what a test charge would do. Notice the festive holiday colors. Would do if placed in field. Okay, oh, what does that mean? I don't get it. Okay, relax. Okay, let's say that we have a big fat positive particle here. All right, it's lots of coulombs, yeah. And we have this negative particle maybe over here. If I take a positive particle and place it somewhere in the field of this big, so there's my little test particle. My test particle is small, tiny, and cute. Yes, you're a small, little, cute particle. Yes, you are. Yes, you are. Now, it's small, so it doesn't have a lot of influence on what's going to happen in this field that's generated by this large positive particle. Oh, it'd be kind of like this. Here's my analogy. It'd be like you, if we were to take you and put you somewhere above the earth. The earth generates a massive gravity field. That if you go into that gravity, which you're in the gravity field now, but let's just lift you up and pull you a couple kilometers high. Oh, that's scary. I know. No, don't close your eyes, okay? Especially if you're afraid of heights. So we put you a couple of kilometers above the earth and let go. No! Bye, Billy. I thought you liked me. I do. Don't worry. You got a parachute. Just use it. Oh, thank you. Oh, yeah. Anyways, so we pull you up there and let you go. Well, you see, you are going to be affected by the field of the earth. Now, Newton's third law says you should also affect the earth itself and pull on the earth, but the earth is so massive and you're so insignificant. You are insignificant that doesn't sound like, I'm sorry, I'm hurting your feelings. Like, I meant in terms of mass, okay? Not as terms of person. You're important, okay? Special. But I'm talking about your mass is so small, that you're not going to have any effect on the Earth and its electric or gravity field. You're just not. You're too small to affect the Earth, but the Earth certainly can affect you. You affect each other, but you can see the result because you're so small. All right, that's my point. My point is, like, you can be anything that you put in the Earth's gravity field. Take it, lift it up, let it go. It's so small and insignificant that would be considered a test charge. Small, but still exists. And we can see what happens if we let go of it. It falls down to the Earth. Okay, same thing here. So we've got this tiny little particle, and we put it in here. It's very small in terms of its coulombs. Big coulomb. So you're not going to really have any effect on you, but you're certainly going to affect that thing. You're going to see that thing accelerate. Which way would it go? Positive. You know, they don't like each other. So this would be pushed away from our big positive field generating thing. This generates a small field. It's like you do. You generate a small gravity field. You do. But you don't see too many things, getting sucked into you. Oh, this marker did because I'm so much more massive than Reza, so wimpy, massive wimpy. You can't even attract an eraser to you. Okay, but you do have a gravity field, but it's really small. So same thing here, really small field, big field. What happens to it? It gets pushed away. That's what Faraday said. Faraday said that a positive field generator is always out. So the field is always out of the positive. Defined as what a positive test charge would do if placed in field. What would do is this would be forced out, it'd be repelled. If we take that same positive particle and put it near this nice big Coulomb producing negative charge here, what would it do now? It would get sucked in toward it because it's attracted to it. Again, a field is defined as what a positive particle would do if placed in the field, and in a negative particle, it would go in. So always here's what we have. Bottom line, positive out, negative in. Out of the positive, into the negative. That's the way field lines are always drawn. Why? Because Faraday said so, and he's the man, the myth, the legend. He set it up. Hey, it's what we all agreed on, okay? I don't agree on it. Well, Billy, someday when you're famous, you can change it all around, okay? But until then, that's what you got to remember. You got to remember that field lines go out of the positive into the negative. Okay? Remember that. Now, because that's what a positive particle would do if placed in the field. All right, let me just show you the field line drawing. What would field lines look like if we had like a positive particle here and a negative particle here? Let's draw some field lines. What would those field lines look like? Well, out of the positive into the negative, 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 out of the positive into the negative. I think you get the idea. So, look, it's a smiley face. Out of the positive into the negative. That's what our field lines would look like. If we were to place two negatives, what would our field lines look like? Out of the positive into the negative. So into the negative, we would be doing this, into the negative, into the negative, into the negative. Now, into the negative, into the negative, into the negative, into the negative, okay, into the negative. All right, now we would start to curve these like this. So there must be some positive region of space out here producing these out of the positives. But when we get close to our two negative particles, we're going into the negative. So notice these field lines, they never cross. Field lines don't cross. And, well, we're going to, we may put a few more in here, but they're going to do this kind of a thing. So out of the positive into the negative. In fact, if you look at these field lines, you can see there'd be a region of space in here. Boop, boop. that you wouldn't have any field lines pulling or pushing on you. You can just kind of hang out between the two, hanging out. And because there's a space between the moon and the earth where the two gravities between the two are pulling on you with equal amount of force, and you would just kind of hang and chill and go,
Oh, there's the moon. There's the earth.
Of course, we all know that you'd have to be closer to the moon to do that because it doesn't have as much mass. Here, I've got my two equal particles, so halfway between, I would be in a spot of equilibrium where I would just kind of hang out and floating, and yeah, pretty fun, yeah, pretty cool. Yeah, so, okay, now what about two positives? What would that look like? Well, what do two positives look like? All right, positive, positive, out of the positive into the negative. So it would just be the opposite. It would be the same lines, but I would just draw them with the arrows going out of the positive, 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 something like that. You still have that space in here where these are exactly the same, same amount of charge, and you can hang out and chill like a Ville. Fun. Fun, 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 till Daddy takes a T-bird away. Yeah. Okay, now, what if we had three particles, like maybe we have a positive, and a positive, and a negative. What would our field line drawing look like now? Well, it would be out of the positive, and just like it was just a second ago, like this, like that, showing the repulsion between these two.
Ew, I don't like you. I don't like you either. It's
Oh, so angsty. And so we would, but here I would get out of the positive into the negative, so it would be something like that. Okay? All right, little smiley face there if you can see it. All right. Oh, and one more thing. Then when we're drawing these field lines, we could show that something is, let's say this is 1 coulomb positive 1 coulomb charge. But over here, I have a positive 2 coulomb charge. I can show that using field lines by the number of field lines that I use. So this is twice the amount of charge. It's going to generate twice the field strength. So therefore, I could show that. But let's say if I show this one by showing, I don't know, maybe four lines coming out, whatever, okay. And so this one, though, if I'm going to show the field of this one compared to this one, I would show how many lines? Twice the charge, generate twice the field strength. So I would show, that's right, you got it, 8. Let's see, 6. Did I do that right? 7, 8. All right, close up. 1, 2, 3, 4, 5. Oh, I'm missing one. Missing one, throw one in there. Okay, so 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8 for 2. So that's another way, another thing that we do with field lines. So if you see field lines being twice as many around one charged particle and the other, that would mean it's twice the field. It's generating twice a strong field. It has twice the amount of coulombs. Okay, all right. Field lines. Pretty cool stuff, huh? Let's wrap this one up and see you on the update next time.